Take a finite group of people. Pick any two and ask how many friends they share. The number changes from pair to pair, sometimes two, sometimes one, sometimes none at all. Now restrict to networks where the answer is always exactly one. Every pair, exactly one mutual friend, with no exception. Then the theorem says, someone in this group is friends with everyone. Always, the same person every time. The proof is 60 years old, and it does not use graph theory. It diagonalizes a matrix. Try to draw such a group. Start with 4 people. Connect them so every two share exactly one mutual friend. You will run out of options fast. Some pair always ends up with 0, some pair with 2. 4 is impossible. Try 5. It works, but only one way. One person at the center, friends with all 4 others. The other 4 split into 2 pairs, each pair friends with each other. A bow tie. Move up to 7. Again it works. Again, one shape only. 3 triangles glued at a common vertex. A windmill. Each time the picture closes, the same person sits at the middle. Forget the small cases. Suppose, for contradiction, that no one in the network is friends with everyone. That is our standing assumption for the rest of the proof. Then every vertex has at least one non-friend, so we can pick 2 people U and V who are not friends. By the friendship rule, they still share exactly one common friend. Call that person W. Now take any other friend of U, call it X. Apply the friendship rule again to X and V. They share exactly one common friend, call it Y. This Y is a friend of V. So every friend of U besides W points to a friend of V besides W. The injectivity of this map needs U and V not to be friends, and that is exactly what our assumption guarantees. The same construction from the other side gives the reverse map, so U and V have the same number of friends. For adjacent pairs, the same argument chains through a third vertex, non-adjacent to at least one of them, which exists again because no one is universal. So every vertex has the same number of friends. Call that common number K. Now count vertices in layers. Start with V. Around V are V's K friends. Now look at any single friend, call it F. The friend F also has K friends. One of them is V. Exactly one more is another friend of V because V and F share exactly one mutual friend by the rule. That leaves K minus 2 friends of F that are completely new vertices, not in V's friend circle. Add it all up. 1 for V, plus K for V's friends, plus K times K minus 2 for the new vertices that each friend brings. That equals N equals K squared minus K plus 1. Combinatorics has carried us as far as it can. The next move belongs to algebra. Build the adjacency matrix A. Rows and columns are the people. Entry 1 if friends, 0 otherwise. Square the matrix. The entry of A squared in row I and column J counts walks of length 2 from I to J. Look at 1. From V1 to V2, the only such walk goes through V3. So that cell is 1. Every off-diagonal entry counts the same thing, the people who are friends with both. By the friendship rule, that count is exactly 1. The diagonal counts walks I to I, which is just the degree K. So A squared has K on the diagonal and 1 off of it. That is one identity. A squared equals K minus 1 times the identity, plus the all ones matrix J. All of A's eigenvalues fall out of that identity. A is K regular, so the all ones vector is an eigenvector with eigenvalue K. On the orthogonal complement of the all ones vector, the matrix J vanishes. On that subspace, A squared acts as K minus 1 times the identity. So the remaining eigenvalues of A are plus or minus the square root of K minus 1. Call their multiplicities R and S. They satisfy R plus S plus 1 equals N. The trace of A is 0 since no one is friends with themselves. The trace also equals the sum of the eigenvalues. Putting both together, R minus S times the square root of K minus 1 equals minus K. Look at that equation. The left side is R minus S, an integer, times the square root of K minus 1. The right side is minus K, an integer. So the square root of K minus 1 must be rational. Since K minus 1 is a whole number, the root is an integer. Call it M. Substitute k equals m squared plus 1. The equation becomes m times r minus s equals minus m squared minus 1. The left side is a multiple of m, so the right side must be 2. That means m divides m squared plus 1. But m always divides m squared, so m divides their difference. That difference is m squared plus 1 minus m squared, which is just 1. The only positive integer dividing 1 is 1 itself, so m equals 1, k equals 2, n equals 3. That graph is the triangle. Every vertex is friends with every other. Every vertex is universal. We assume no vertex was universal. The triangle is the violation of that assumption. Contradiction. An apex must exist. So an apex exists. Once it sits at the center, the rest of the structure forces itself. The non-apex vertices fall into triangles glued at the apex. A windmill. Every finite group, where every two friends share exactly one mutual friend, is a windmill. Always. A small local rule, repeated for every pair, forces a single point of global structure. The matrix saw what graph theory could not.